Hey, good morning, everyone. We got Kirsten here, we got Thomas here, we got Rajvi here, we got Michelle, we got Joseph, we got Michelle again, we got Hudson, we got Sierra, we got Aisha, we got Joseph, we got Meath here. Who else is here in the chat? Say hey, Mubot is awake. Let's throw out 100 points. We've got a few questions. I got sent some questions from a Tool 1 student. We've got the twin bursts question, Stat Tool 1 twin bursts. That's chapter 14. What shall we do to start? We got chapter 14 twin bursts. What should we do? Put those questions. Kirsten, so good to see you. Stat 201, chapter 14. Students' absence from school. I think that's chapter 14. Chapter 16, a company being sued. Let's do that. You're here, Meath. You get first question. Chapter 16. The twin burst, is that chapter 15? Company being sued. There we go. Story A, Story B. What chapter is that from again? Okay, let's get the company being sued. Okay, so much exciting news. Wait, I'm going over to Canvas. I got a really great message from Data Camp this morning. So, could you go over chapter 17? Yeah, Kevin, there's chapter 17. Kevin asked about Story Story. Let's put that next on the list. Statue on chapter 17. Ooh, you're near the end. Which one? Chapter 16, Rajvi? Let me know. We do. Aisha says, can you go over chapter assignment 6 or 474? Like transforming data and beginning of it. I'm so lost. Chapter ES 474. Assignment 6. Transforming data. Awesome. Do transforming data. Vital statistics report. Everyone's ready. They're like, oh, got some questions. We'll put that up here at the start. Statue 1, chapter 16. Vital statistics. Copied it. Hey, got that. Ratio and factor again. What about ratio and factor? Good question right there. Ratio. Oh, are you talking about with the RMSEs, Sierra? Are you talking about that? Let me put that on here, Sierra. Thank you, Sierra. We're gonna do Tool 1 to start, then we're gonna hop to the advanced stuff. Are you talking about the RMSEs, which would cover both classes? Nice. Dylan, great work, man. Dylan, thank you for those messages. Another group I was talking to too, but great job working on that. Gave you that hint right there on how to get it done. Just showed you. So yeah, please, groups in 475, message me if you're stuck. Dylan messaged me that he couldn't get into a TISBL. Was doing with like Lubridate methods, but we did it with some FQP3. I sent him a hint on like, showed him I had like mutate. What I have? Mutate. Can't remember the order. I've now done it 3 times, turning it into a TISBL. It's a little bit of a task. Oh, I did the string concatenate. I told you that. That made it easier. So yeah, good questions right there, Dylan. Thank you so much for asking. If you get stuck, just ask. So glad. And Sierra, are you talking about the... Oh, wait. How far off should a linear model be? My RMSE is 1300. I've done it several ways, and I get the same answer. So Sierra asked about 474 RMSEs. To Sierra, that question. When you're doing RMSEs, they're data dependent because... Let's put it this way. I'm going to turn off music for a second. So while I get chapter 16 loaded up, if I had an RMSE on the price of a car of $10, would that be a large or small RMSE? So think about RMSE. RMSEs always need context. If I had an RMSE for price of a car of 10, would that be large or small in the chat? And then we're going to do some chapter 16 right here. So an RMSE for price of a car is 10. Is that a large or small? It'd be very, very small. Because that's saying when I predict the price of a car, I'm typically off by $10. But if I go to a restaurant and my RMSE is $10, and let's pretend it's not some super fancy $500 plate restaurant, if we go to a restaurant like Cheddar's and my RMSE is $10, that's pretty large because that says when I predict the price of the bill at a restaurant, I'm typically off by $10. Now, I mean, 10 at a restaurant, I don't know, typically off by 10, like I think the bill's 30 and it's 20. It's a pretty big difference. I could have said 100, and then for price of a car, 100 is not that much to be off by. Like we think the car costs $21,000, costs $21,100. So being off by 100 for the price of a car is not that much. Being off 100 for the price of a restaurant is a lot. So anytime we look at an RMSE, And this is Stats Will in question. For 100 points, anytime we talk about data, what matters? Think of it, something starts with a C. Every time we talk about data, if we're talking about an RMSE, like a typical miss, and we're saying my typical miss is this, where we have a typical miss, it's the context. It goes back to the context. So $100 off for a restaurant is a ridiculous amount. $100 off on average for a car is not that big of a deal. So Rock knows. He knows all the answers to the questions in the class. So to Sierra's question, how far off should an RMSE be for a linear model? What are we... Is that the demand one? Are you doing demand? Yeah, if you look at the range of demand, it ranges from like, I think 4,000 to 8,000. Yeah, with bike demand, like, so what you could do, you could pull some 320 knowledge. You could look at the naive model. The naive model, you could calculate using the mean of the Y. So you could, don't worry about, the whole goal of this assignment is not to find the best model in the world. The whole goal of this assignment is to understand how to make models and know what these values mean, that when you predict the bike demand, you're typically off by this amount. Like my typical miss when predicting bike demand is about 1,300. Then also look at the residuals of it to see if they're kind of spread out, which we ended class with yesterday. You don't have to do that, but that'd be some good follow-up analytics. Like, you know, in 475, we do looking at some residuals of the model to see, like, does it have a constant typical miss, or are we getting some extreme values that are kind of throwing it to the, like, extreme? Awesome stuff right there, everybody. I think that answers Sierra's question right there. Does that make sense, Sierra? So you're not going to get graded on how good your RMSE is. You're going to get graded on how well you interpret your RMSE. So that's what we're focusing on now. And then, truthfully, I think you're right, Sierra. We are going towards, like, we want to make super awesome RMSEs. Also, for the 475, do we get 2 drops? Yep, 2 drops. I think on Canvas doesn't count. We'll make sure the 2 are in there. Good question, Aisha, right there. Is it normal to get a way smaller RMSE if you Yes. RMSE is scaled by your variables, so you'll want to undo the transformations, Kirsten. If you did a transformation on the Y, you'll want to undo it. And Kirsten, if you're interested, now you don't have to do this, there is a way to do tidy models, and tidy models would back transform for you and get the units back. It would be, don't go unless you got just spare time. But one of these days I want to implement tidy models into the class, and I've got some really big, exciting news. It looks like DataCamp has an LMS integration. I've been contacting them about that because I would love it if, to help people learn how to code, we integrated DataCamp into Canvas. So that way you could do DataCamp quizzes, and like you would get generated questions that would quiz you and see your knowledge, and you'd get a bunch of attempts. So like literally you'd be doing the quizzes in Canvas to practice coding. And I think that will take coding to another level for people. I know, right, Shreya? So it would be like, you'd be like, oh, I'm going to go do my quiz. And it'd be like a DataCamp quiz in Canvas. I'm having conversations with DataCamp, reached out to them, and really want to help people out. So a lot of exciting news, a lot of big upgrades, thinking about the best ways to help people practice, because it's one thing to watch me code. It's another thing to sit down and like wrestle with the code, because you see how many times I get stuck? Woo! Woo! Let's hop into that first question of the day. Thank you so much, everyone right here. We got a company being sued for discrimination. Let's go find out about this. Oh, thank you, Shreya. 100 point Shreya right there. I make it look easy till I get stuck. And then it's like, well, if Brian can't do it, then maybe Dr. Petrie can. And then he probably can. Dr. Petrie and Adam Spanbauer, some of our best coders. And Dr. Me. We've got a lot of great coders. And Bogdan Bachescu and Dr. Wei. We got so many. Okay. First question of the day. A company is being sued for job discrimination because only 13% of the new hires were immigrants, where 49% of the applicants were immigrants. Is this strong evidence that the company's practices are discriminatory? Well, just going on this alone at the top, it does look to be. Now, when you think about this, this gets to the idea of nulls and alternatives. How would you define a null hypothesis to someone who doesn't do statistics? How would you define a null hypothesis? How would you, someone doesn't do stats and you say, well, a null hypothesis is basically our this. It's our what belief. So what would a null hypothesis be? Someone doesn't do stats. What would you talk to them about a null hypothesis? What would that be? What is the null hypothesis? Say, this is my null hypothesis. Well, what does that mean? What does it mean to say null hypothesis? How does that work? Thoughts on it? We'll get a moment longer. If I say I have a null hypothesis, kind of an assumption, it's what we believe to be true. Sierra, that's a great answer right there. An assumption, what you believe to be true currently. So we could say current slash, or we could say current belief. It's what I start out believing. So an assumption works, right? That it's like we consider true until we have evidence against it. Meath, great answer right there. Both these answers are awesome. So null hypothesis is your current belief, assumed to be true unless there's evidence elsewise. Like, I always like using this example right here. Like my friend Nathan, crazy guy, he's saying the world is flat. He says we're on this, he says there's an ice wall over here. I say, Nathan, man, what you talking about? So what would I try to supply to Nathan to convince him the world's not flat? I say, look in the sky, look at the planets. He says, well, every other planet's an oblate spheroid, we're not. I say, okay, well, let's do some mathematical calculations. I'm trying to offer him more and more what? What am I trying to, I say, look, we can do a calculation with the rays of the sun to show that the Earth is not flat, because if the Earth was flat and the sun is beaming down on it, then the way the sunlight should go into a hole at all points on Earth, if you were to measure it at different areas at the same time, you would see the same sort of angular on the side of the wall of the hole. See the same sort of angular light, but you don't. Because think about if there's a sun up here, and the sun's beaming down light, then if the Earth is flat, you're going to see the same sort of light on the hole. KP, good to see you here. But if the Earth is a sphere, which we have strong evidence that it is, the Earth is a sphere, then over here, if you put a hole down here, then you're going to see a different angle of light than if you put a hole down over here. It's going to do it differently. So what are we offering them? What are we offering them? What are we offering them right here? We're offering them a what to their belief. They have a current belief. We're offering them an alternative hypothesis. And we need to give them what for this? What do we need to give them for our alternative? They have a null hypothesis. They have an initial belief. We say, let me give you what for something else. Say, let me give you what for something else. Or I could look at a fulcrum pendulum. That'd show the movements of the Earth. So if you know, a fulcrum pendulum hangs up high right here, and then down bottom it sways and actually mimics the move, or can show the movement of the Earth. Pretty crazy. We're offering them evidence. I wouldn't, would that show the Earth's round? No, it would just show the Earth is moving. It's so interesting to me when I hear people say the Earth's not moving because I don't feel it. I'm like, just, have you been in a plane? Have you ever been flying in a plane and fall asleep and wake up in the plane? You might hear some noises. You can hear the wind gusting around you sometimes, but we're in an atmosphere on Earth, so it's pretty interesting to me. We need evidence for alternative. It's pretty interesting. People form different beliefs, so we have to show them evidence for alternatives, and that's what we do. We get the data. We say, here's some data. Here's reason to believe our alternative in our scientific model, and you should reject your initial belief because we have evidence for an alternative right here. Keywords we need to know: the idea of reject, the idea of fail to reject. Those are terms you need to know, like you reject the null, you do not reject the null, which is fail to reject, you have evidence for your alternative, or you do not have evidence for alternative. So when you think about one-tailed versus two-tailed test, one-tailed test means we're showing evidence in one direction. So we're trying to show evidence that the company is discriminating here. So the test is one-tailed because they wouldn't be sued for too many immigrants being hired. They're only being sued for discrimination right here. Now, here is a type 1, type 2 error. Now, who knows how we do type 1, type 2 error? In a type 1 error, I'm going to throw 500 points if anyone knows this. The what is what? So this is the way to memorize it. In a type 1 error, the what is what? Does anyone know it? My 201ers, former 201ers. In a type 1 error, the what is what? Who knows how to finish that sentence? In a type 1 error, the null is true, but we reject it. Great job. Anin right there. Good to see you. Great to see you. You're also. Oh, thank you so much. Oh, wait. Yeah, you're a mod and everything. Oh, let's throw 500 points. Were you... I'm trying to remember. Nin, so good to see you. Thank you so much for all those kind words you have right there. Awesome to see you. So the null is true. Correct right there, Shreya. Good work. The null is true, and we reject it. Now, you ready for the second one? In a type 2 error, the null is, think about what letter I'm making. The null is what? And we what to what it. So finish the sentence. Ready? In a type 2 error, the null is this, and we this to reject it. Ooh, wait. Oh, Shreya, no. Except means we believe it. Yes, Shreya got it. Shreya recovered right there. The null is false, and we fail to reject it. How many F's are there in the type 2 error? If you think about type 2 error, where we say the null is false, and we fail to reject it. No worries, Shreya. The null is false, and we fail to reject it. How many F's are there in the type 2? Shreya, I'm telling you 500 points. Maybe smile and laugh right there. There you go. The type 2 error has 2 F's. The null is false, and we fail to reject it. And we only talk about the null hypothesis in these. So this is the best way to memorize these. These questions are on the test. In a type 1 error, the null is true, and we reject it. In a type 2 error, the null is false, and we fail to reject it. If you practice that and you even have your cheat sheet right here, I swear, I've seen people during the test, when we would give it inside of alumni, I've seen people be like I've seen people like mumbling to themselves and like doing this. And I'm like, yes, 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 yes. You know it. So in a type 1 error, the null is true, and we reject it. In a type 2 error, the null is false, and we fail to reject it. Let's go take a look at the question. Okay, so the null hypothesis is what we would believe about the company. The null hypothesis is company is innocent. This is the way it works in court cases. We have the company is innocent until we have evidence of guilt, and the alternative would be company is guilty. And I know in a court case, you generally say innocent or guilty, not guilty, so we could say not guilty, but we'll just go with this right here. So in a type 1 error, what is the company? Just be careful. Say it with me again. It asks about type 1 error to start. In a type 1 error, what is the company? Just tell me what they are. Don't worry about telling so much yet. Just if a type 1 error were to happen, talk to me about what is the company. Just talk me through what is the company. Error is going to be an error. So let's just figure out what the company is so far. The company is innocent because in a type 1 error, the null is true. So you say in a type 1 error, the null is true. But we're going to what the null? So what would this mean? This means the company is innocent, but we make an error and we reject it. Great job, show you right there. We reject it and we say we have evidence they are guilty. So this would be when an innocent company is found guilty. Because the null is true, they are innocent. That is a fact. The company is innocent. So it is deciding they are discriminating when in fact it is not. Now it's easy to do the type 2 error right here because it's just going to be the opposite of it. It's going to be the company gets away with discrimination. So it's deciding the company is not discriminating when it actually is. We'll just talk about that briefly here to once again practice saying it. In a type 2 error, the null is false. So this is false. Like that is a false statement. But we are going to fail to reject it, which means we hang on to it. So it would be true that the company is guilty. Like the company is guilty. That's a fact right now. In a type 2 error, the null is false. It is false that the company is innocent. It is true that the company is guilty. So we are going to say that we fail to reject the null here in a type 2 error. Now, we don't know we're making this. That's why it's called an error. So this would be the company gets away with discriminating in a type 2 error. We don't know we make it. I've always had people say, well, why would we do that? And it's like, well, you make errors in court cases. People get away with crimes and people get put away for crimes they didn't do. It's really bad. In context, what is the power of a test? Now, mathematically speaking, and I've just done a lot of work with power lately, power is the ability to correctly reject the false null. Definition of power. The ability to correctly reject the false null hypothesis. And power is mathematically 1 minus beta. What is beta? Does anyone know what beta is? 500 points if anyone knows what beta is. Beta is the probability you make a what? Does anyone know? Hint, if you know what alpha is, I'll give you a huge hint. alpha is type 1 error rate. Yeah, your type 2 error rate. What percent of the time you make a type 2 error? Great job, Meath, right there. So, yes. Alpha is type 1 error rate. Beta is type 2 error rate. So think about this. Type 2 error is where we fail to reject the false null. So it's failing to find results. So power is not making type 2 errors. That's what it is mathematically right there. Power is not making type 2 errors. So when we think about what power means, it would be being able to find that the company is guilty, because if we fail to reject the false null, the company is guilty and gets away with it. It's basically not making type 2 errors. So it's not doing this. It's the complement of this, because 1 minus type 2 error. So the power is the probability of correctly determining the company is actually discriminating. Remember we said power is the ability to correctly reject the false null. If the null is false, they are discriminating. And the ability to correctly, so it's got a lot of that right there, the ability or probability that we correctly reject the false null. If the hypothesis test is tested at the 5% instead of 10%, how will this impact power? So there's three things that impact power. The three things that impact power are alpha, sample size, and effect size. If this company were to refuse to hire any immigrants, would that be strong evidence of discrimination? Like they just don't hire a single immigrant. This company, would that be strong evidence, yes or no? Like you look and you say, this company's never hired an immigrant. Immigrants are applying every day and they just will not hire a single one. They've never hired a single one. Like thousands of immigrants have applied and they will not hire any. Would that be strong evidence? Yes. And so which one of these would that relate to? The alpha, the effect size, or the sample size? The alpha, the effect size, or the sample size? Which one of those, like the actual distance it is away from the null hypothesis? Like the null is that they're not discriminating. The alternative we're showing evidence for, or trying to show evidence for, is that they are discriminating. If they never hire a single immigrant, that would be talking about the what of what they're doing. The sample size, the alpha, or the effect size? Which of those relates to the company has never hired a single immigrant? The effect size, yep, that's the effect size. Effect size is the true difference between the null and the truth. And if there's a big effect, like let's say you're trying to see if a student knows a topic and the student has superior knowledge, well, then if you're seeing if they have above a 70 knowledge, well, if they've got 100 knowledge, it'd be really easy to detect. But if they're right here at a 70, it'd be hard to detect if they're above a 70 because they're so close. It'd be a small effect, like they're very close to what you're testing. So if the company's only discriminating a little bit, it'd be hard to detect. But if they're super discriminating, that's a big effect size. Now, sample size is pretty obvious. If we collect more data, it increases power. Also, alpha, if alpha goes up, power increases. All of these right here have an inverse relationship to beta. Beta is your type 2 error rate. If those go up, beta goes down. But power is 1 minus beta. So if beta goes down, power does what? If beta goes down, so if alpha size goes up, if alpha size, yeah. If your alpha goes up, beta goes down. If your sample size goes up, beta goes down. If effect size is higher, we don't really control it, beta goes down. So if beta goes down, 1 minus beta would do what? If beta goes down, 1 minus beta would do what? No worries, KP. We talked a little bit at the start. If beta goes down, so if any of these go up, beta goes down. But if beta goes down, 1 minus beta would go up. Yep. It's just the complement of it. So this basically makes your test more powerful. So does this make sense? Like this is how the chart goes. It's like all three of these going up does this to beta. If those go up, beta goes down. If beta goes down, then 1 minus beta goes up. So it's like a flow chart. It's like if any one of these three go up, beta goes down. If beta goes down, then 1 minus beta goes up because it's inversely related. It's literally the inverse. So when you look at this, it says on this question, if the test is tested at 5% level instead of 10%, so alpha did what right here? Did alpha go up or down? It says if it's tested at 5 instead of 10%. So if it's at 5, if it's down here, instead of 10%, alpha did what? So alpha did what? If it's tested at 5 instead of 10, then alpha did what? It decreased. So the power of the test would decrease because the significance level decreased. And over here we showed increase, but it stands to reason if these decrease, then they would also decrease this because those are positive related. Like if those go down, the other one will go down. So the alpha follows the power follows the alpha, I should say. And the lawsuit is based on 44. How does this compare to 15? How is 44 to 15? 44 to 15 is what? 44 up here to 15 is what? And this is talking about the sample size right here. So they're talking about based on 44 instead of 15. So what is that? Good to see you here, DD right there. Awesome. Good to see you in the chat. Checking out those points. We're gonna throw DD 1,000 points. I'm gonna make you a legend here, DD. 1,000 points for DD in chat right there. So if sample size, great job, Meath, right there. Yes, this is going to be the power test is higher because the sample size increases. Wait, did we miss a question? Oh no! Oh, the one-tailed. There is one. Oh, because it wouldn't be too many. There we go, right there. You're welcome. Thank you. I'm sure that. Woo! Got scared. I was gonna miss one. Woo! Got scared. Great work right there, everybody. Excellent job. Let's head over. We'll do another question. Let's do it. It is time for some 1997 vital statistics reports. How does our people feel like they understand type 1, type 2 error a good bit better? That is a great review question right there on type 1, type 2 error. How do people feel about that question? Type 1, type 2 error. Hudson's asking about some jokes in the chat. What joke will it be today? I used to think correlation implied causation. Then I took statistics class. Now I don't. Sounds like the class helped. Well, maybe. Correlation is not causation. Correlation is not causation. Good to see you here. Yes, Swamp. Good to see you here. More jokes in the chat. Where's the vital 1997 vital statistics report? Where is that one? Someone said it was chapter 16. It might be 17. If you asked about the vital statistics report, we need new jokes. Share, think of some new jokes, and we'll put the new jokes. If you asked about the 1997 vital statistics report question, let me know. I've done that one, but I don't see it in chapter 16. It might be 17. So we're gonna go to store A, store B. Oh no, it was a student asked about it. Okay, we got twin bursts. Let's do store A, store B. Kevin asked about that. And I can't find the vital statistics report. Maybe they removed it. How's everyone doing this morning? We've got another hour or so. A little less than an hour. Here we go. We're going to do some store A, store B. We're going to do confidence intervals for the difference between two means. Store A. Here, I found it immediately. Okay. Just finished the assignment. That's great. It's chapter 15 quiz. Nice. Thank you so much, Raj V, right there. Store A, store B, and then we're going to change this to chapter 15. And let's do the store A, store B right here at 31:25. Let's do it. Okay. So a lot of these last few chapters really boil down to knowing your what. This is where you have to know your what to do these problems. Hint, it's up here. The last two chapters really boil down to knowing your what. The last few chapters really boil down to you must know your what to solve these problems. You must know your what to solve the problems. The only way to solve these last few chapters, and when you get to the test, is you have to know your what. What do you have to know? Does anyone know? Or am I the only person? Notation, 100 points right there. Kevin and Meath, great job right there. You have to know your notation. So what is this? What is this first one? I'll highlight it in yellow. What's that? Like, we could read the problem. It'd probably tell us something, but we should know the notation right here. What is N? It says store A N 85. What is that? What is that? That's the sample size. That's how many stores they went to. Great job, Meath, right there. And Kevin and Michelle, that's the sample size. What is Y bar? What does Y bar represent? What does Y bar mean? So they're measuring something about the stores, and that's the what for the stores. Let me go take a peek again. What were they measuring? So they're asking about purchase amounts at the store. How much like amount they purchase. Sample mean. Great job, Meath. That's excellent. Yep, that's the sample mean. Means something, Kevin. Yep, it's the sample mean because there's a small difference between Y bar and mu. Mu is the true mean for a population. Y bar is the sample mean. So sample means come from a sample size. Mu is from a whole population. So there's a small difference in like terminology where we talk about mu being for the whole population. It's a Greek parameter or Greek notation for population parameters. And then the sample mean Y bar. The bar literally means the mean of it. And so if you do something like X bar, that's mean of variable X. After pre-proc data, but not transforming demand is normal, do I need to... I wouldn't transform demand. That's my personal opinion, KP, right there. I wouldn't transform demand. If you do transform it, you need to untransform it afterwards because your RMSEs and stuff will be in different units. So be careful. Not the end of the world. Just make sure the company understands what you do. Talking about 474 right there. I personally, since it's mostly normal, I wouldn't transform demand. Personal opinions. Personal opinions with Brian. Last but not least, we have standard deviation, which is the variation. Standard deviation is going to control how spread out the distribution is. Bigger standard deviation, bigger standard deviation, bigger spread for a distribution. So this wants us to do a hypothesis test right here. Let's look at the hypothesis test. Every hypothesis test has a this and a this. Cracking up Michelle in the chat. Every hypothesis test always has a blank and a blank. And you see it right here as the naught and the A. Every hypothesis test will always have a what and a what. Every hypothesis test will always have a what and a what. A null and an alternative. A null and an alternative. Great job practicing right there. So when we do hypothesis tests and we write parameters and actually do it in statistical notation, here's what we have to do. You ready for this? The way to write your null and alternative is to first go right here and say the null states. That's how that reads. All this reads is, if you read it as a sentence, is the null states. Now we need a parameter. So we need a parameter, and then we say equals hypothesized value. Okay, so this is how you write out your null hypothesis. And we spend a lot of time practicing writing the null because the alternative will be very easy to write next. Now, if I were to ask you, I believe students have a 3.5 GPA at UT. Can anyone for 500 points write out that null hypothesis about what Brian believes? Now be careful, it's not quite the question we're doing, but we're going to show how this all relates. I believe the average GPA of students, hint, average GPA of students is 3.5. Can you write that null hypothesis right now? Like the null states something equals something. So Brian believes at this moment, Brian's currently held belief, he believes the true mean of GPA of students is equal to 3.5. Think about how you'd write that. We'll do 2 questions on here on this. These are like little mini lectures doing the problem right here to make sure you understand how to write the null. So what is my parameter and what is my hypothesized value? So I'll repeat the question again. Listen for the parameter. Close, Kevin. Super close. Close, Meath also. Very close. Kevin, you didn't have the parameter. And then Meath, we need to move over the number a little bit. And then you almost have the right parameter. Well, you're getting closer. So with all notation, it would be H sub O mu equals mu naught. And why is it mu? Very close, Meath. And so why is it mu though? Because it's GPA, mean is what? Because it's GPA, means are what? So think about, since it's because for GPA, it's quantitative, right? Because it's the mean GPA. P is for proportions for categorical data. So that's a good way to tell right there. I'll do one of those in a second, so get ready for the next one. So if we were to write out the notation in this, Brian believes the true mean of GPA for students is equal to 3.5. Does that make sense if I say this as a sentence like, my currently held belief, my initial null hypothesis, is that the true mean GPA for students is 3.5. This is my hypothesized true mean. That's what the hypothesize stands for right there. So then think about this next question. Brian believes that 70% of students love Taco Bell. How would you write this one? So use your previous knowledge because you're almost there on the last one. How would we say Brian believes that 70% of students love Taco Bell? Which it should be higher. You could test to see if it's higher. How would you write out Brian believes that 70% of students love Taco Bell? How would you write that one out? So you need to do the null states, some population parameter is equal to a hypothesized value. So Brian believes that 70% of students love Taco Bell. This is a really great practice right here. I always want people to do things and then we get practice. So Brian believes that 70% of students love Taco Bell. What do we get? Close, Kevin. You're so close. You're so close. You're so close. Meets, you're so close. But you're close. Super close. Super close. Do you want to get one more shot? Super close. You're both really close. So it would be both really, really close. The null hypothesis states that the true proportion of students who love Taco Bell is 70%. Close. And Shreya right there. Shreya got 500 points. And we could call it P1 for like group 1. And so that would work right there. Generally, since we're just doing one proportion, the true proportion. And so there we are right there. The null states that the true proportion. So the first part is what you're making the claim about. Does that make sense right here? We're making the claim about the true mean. We're making a claim about the true proportion. And if we look at this question, what is this question making a claim about? The what? Oh my gosh. The what between two whats? This question is making a claim about the what between two whats. So think about like the first one we did was making a claim about the true mean. The second one was making a claim about the true proportion. This question is making a claim about the what between two whats, the difference between two means. Because that's what we're talking about. It's like, I believe currently that the difference between two means is equal to 0. And so the right answer, the null always has the equal sign also, because we're always making a claim that it's equal to a certain amount. Great job right there, people practicing, remembering some knowledge right here. Great job, Sierra right there. And Treya too. So you can see right here, the null is currently stated as one of these. And then the alternative, all we do is change the sign. Can I get some all you do is change the sign in the chat? For the alternative, you just change the sign, and they are trying to see if they're equal. So if that's what they're testing, the alternative would be that they're not equal. And all I did was change the sign. If you look at the difference between this, you write your null, and that's why we focus so much on writing the null, and then you just change the sign to whatever you're testing. Do you want to see nothing but none? I love it right there, Shreya. Nothing but the sign changing thing. Shreya, we're making that a quote of the day. Shreya getting some quote right here, quote 266. Check it out in the chat. Quote 266 from Shreya right there. Nothing but a sign changing thing right there. Just change that sign. That's all you do. Okay, so now we got to compute the t statistic. This is where the math's going to come into play. So we have to do the formula. Okay, let's write this down. Okay, it is y bar 1 minus y. Wait, is it store A or store B first? Okay, it's A minus B. You have to look at the order by which they're subtracting them. It is A minus B. That you will get it wrong on some questions if you do not do it properly. If anyone wants to check my work with me, that would be much appreciated. Please help me out. I do make errors every once in a while. Oh my gosh, writing the numbers in. So we are currently putting the notation. There we go. And I'm going to write the notation below this. All right. Okay. Whew. Well, let's solve this. You can read my little bitty handwriting right there. 41 minus 50, that's a difference of -9. We'll use that later. 20 squared is 400. 400 divided by 85, that's that. 18 squared is 340 something, 320. Divided by 81. Oh, what? No way. Whoa.
Wow.
And that's going to be basically 3. So it's going to be like negative 3.1? Something like that, negative 3.1. Okay. 41 divided by 50, minus 50. There we go. Negative 3 point. Nice! Shreya beating me to the answer. Wow.
Wow.
That's a lot of wows right there. Shreya, 500 points. Double checking my work. Getting the answer as quick as Brian right there. Great work, Shreya, right there in the chat. Awesome. Thank you so much. I really appreciate those things because you don't know how many times I'm like, I made an error. R helped. Oh, yeah. It's a lot easier. I would do it in R, but I swear I've had people be like, you know, sadly, I can see how, like, if we don't use R in a class, it could be more confusing. But it's so much better, right? You just put the numbers in, make sure you put them in the right way, and then solves it all out, everything down to the decimal. So now we need a p-value. I'm going to show you how I got this here in a second, but I want you to think about this. I want you to think how I know that. We're going to say I got it right. We're going to cross our fingers here, then I'm going to show you how I got that. We reject the null hypothesis. There is evidence for the alternative. Now, let's talk about this in a second. Did we get it right? We did. How did I know this p-value? A lot of people say, how in the world can you get a p-value by not using the applets? How could you ever do that? Well, T's and whats are very similar. T's and whats are very similar. What is very similar to a T? Like a T and a this are very similar with high degrees of freedom. T's and Z's are very similar. So I want to show you how I got this answer, then I'm going to show you how to get the answer. So how I got this answer was I said the following. I said, I know for z-scores that if I go out to 3 standard deviations, that this will cover what % of the curve as a decimal. Ah, you're right, Meath. Meath, 500 points. You're already seeing where I'm going with this. What % as a decimal is covered on the curve right here? Meath, great work. You're already seeing how I did it. So what % is covered on the empirical rule on the z-scores with this right here? 99.7, 68, 95, 99.7. Sierra's got right there. So what % would be outside of this? The outside area would be 0.003. Now, remember, on our problem, we were a little bit further out. We were at negative 3.05. And this is absolute value because we're doing the does not equals test. Let's show it here visually. If you're doing a t-test, you have to know the degrees of freedom. The degrees of freedom for the test are a complicated formula for the 2-sample t. We do not find them by hand. The degrees of freedom for this one is given to you of 163.47 rather. So we go here and we enter in the degrees of freedom, which control the shape of the t. There's the shape of the t. Then we enter in our t statistic, and we already are doing the two-sided test. We enter in negative 3.05, and it gave it to me. I was close enough, and funny enough, we could have just entered 0.003. So good to see you here, Jessica. I think we did the first question. Did you ask about the first question? I think we did. This is the greater than test. This is the less than test. And this is the two-tailed does not equals test right there. So if you're looking to get the answer for your question, make sure you go to the applet and you would use the two-tailed test, which shades both sides of the curve. As you can see, if I put in values where it's easier to see, the positive or negative,
It doesn't matter.
we just shade both sides of the curve right here. Awesome. Yep. So this is how we get the p-value right here. And I did my little drawing to kind of show what we'd be seeing. And we see something similar. It's just very hard to see that area on the outside. So try doing those drawings to see if you can get it. Now, there's a phrase at the end of this. We always say, I reject the null, I have evidence of the alternative, or I do not reject the null, I do not have evidence of the alternative. Let's write that. The only phrases are, I reject the null, I have evidence for the alternative, I do not reject the null. I do not. Does everyone notice how these are paired together? If you reject the null, you do have evidence to the alternative. Better grammar right there. If you reject the null, you do have evidence to the alternative. If you do not reject the null, you do not. You can say, I do reject the null. I do have evidence to the alternative. Sound like I'm at my wedding. I do. So with this right here, if you do reject the null, you do have evidence to the alternative. If you do not reject the null, you do not have evidence for alternative. And what does reject mean? It means you don't think it's true anymore. Like, I throw my null away. I'm taking that alternative with me. I don't throw my null away. I'm going to not have evidence for my alternative because I don't reject my null. If I did reject it, it's because I had evidence for alternative. So hopefully this right here can help with the last one. These are the only pairings we should use. So when we see down here at the bottom, I reject the null. There is evidence for alternatives or sufficient evidence. That is paired together properly. The only other possible one is I fail to reject the null, which means I do not reject. That's just another phrasing. Let me ask you this last question on this one real quick. I failed to go to the mall today. Translate Brian's English right there. Brian what? I failed to go to the mall today. Translate what that means. What does I failed to go to the mall today mean? Which we talk weird in stats. But when someone says, I failed to go to the mall today, you say, hey, did you go to the mall? I failed to go to the mall today. How does that translate? If I say I failed to go to the mall today, what does that mean? I did not go to the mall. Yeah. So if we say I fail to reject the null, so I fail to reject the null, that means you do not reject. So I did not do this. Fail to do something is to not... Fail to do it is to not do it. Great job, Kevin, right there. And Meath right there. Awesome work. So if I fail to reject the null, then I did not reject it. It's just... I fight the good fight to get rid of that stat wording right there with just having people talk normal. Like, I do not reject the null, but if you do stats, someone's going to say fail to reject. If you're doing chemistry, physics, or something, someone's like, I fail to reject the null, and you have to know what that means. You got to know. We teach you the stats words so you can do the stats stuff, and you can just say to people, I didn't reject the null if you want. Anyways, back to the main screen. I go for application in business sense. So if you're a business analytics student, we would probably say to someone, yeah, we didn't, I don't know, I wouldn't say reject. I would say like, yeah, it looks like that's believable. That's how I would interpret it to a business person. I'd say, yeah, we were testing to see if 4 was the true value, and looks like it could be. We have 1997 vital statistics, twin burst, and student absence. We got probably time for at least one more of those, and then we're gonna switch to a different class. Right now, just say which one you want in the class. First person to say it. Twin burst, student absent from class, or 1997 vital statistics. Which one of those do you want to do? If you're here right now, you get to pick from the ones we have on the screen. 1997 vital statistics, twin burst, or student absence. You pick, we do. Let me get the questions ready to go over here while you pick. 1997, you said first right there, Rajvi. Awesome. And that was the next one on the chat. Okay, that's chapter 15, 1997 vital statistics. Let's do it. I'll try to get the second one done here too. Thank you, everyone, Michelle and everyone. And I do have videos over the other ones. I always try to do as many as we can live right here. Do as much as we can live. And thank you, everyone, for all your hard work. Because I do understand Stats 1's a little tough at the end. This is the meatier part of the course. Wait. This is 2001 vital statistics. Is this the same question? Rajvi, is the vital statistics report also the twin one? Is it the same one? Did we just luck out? I have 1997 vital statistics report. Did they change because I'm seeing, is the vital statistics report the twin one? Can someone confirm in the chat? I think yes. Wow, we win.
Wow.
Oh my gosh. Doing the both right here. Let's just call this twin burst. So, yeah. Everything stopped making sense. No, Michelle, no. I like that goofy smile right there. Michelle, we're going to make that another quote of the day. Michelle, quote 267. It's tougher. It's tough. And that's why I always encourage everybody to get all those grades in. Mubot remembering, Mubot having some fun. Okay. Let's start up this question right here, and we'll make things make more sense, Michelle. Let's do this. Here we go to the main screen. Here we go. Sound like I'm like a cheer, like, here we go, statistics. Here we go. Here we go. Stat tool on. Here we go. Let's do the question. Okay. So in this question right here, we are doing a hypothesis test on the true proportion. So with this, we have to know what the conditions are. Condition 1! What's condition 1? Anyone know condition 1 when we do a hypothesis test? It's always this. Every time you do it, it's always this for condition 1. Random. Did we random? You about loving the randomness right there. Did we randomly select the observations? So condition 1 is always random. Did we randomly take the observations? Are these random twin bursts? Maybe. Maybe. I don't know. Probably. Question 2, or condition 2. Yeah, I think yes. Probably. Is it safe to assume? I'd say yes. It's asking about all 3, but just it summarizes it quickly. Condition number 2 is what? Now, this is a weird one, which I usually don't go into much detail on. It has to deal with finite populations and the amount we take. We say random, and then the second condition is what? Sometimes they break it apart into random and independence, but Jessica's got right there, less than 10% of the population is sampled. If you're wondering about it, it's a complicated condition that deals with finite populations and the error we incur. I've read some big articles on it. It's rather boring in my opinion, and if I find it boring and I do stats, I don't think students are going to find it much more interesting than I do. But the best way to memorize it is we sample less than 10%. So the question is, are these 574 individuals they take a sample from less than 10% of all populations of teenage girls giving births? And I'd say yes. That means that there's more than like 5,740 teenage girls giving birth, and we sampled less than 10%. Does that make sense? What this means to this, say, that sample right there is less than 10% of the population we are trying to measure. So we've taken less than 10%. You look at the sample size, and then you might have to theoretically think about it. If I sample 10,000 UTK students, would we pass the 10% condition? So Brian samples 10,000 UTK students. Would we pass the 10% condition if we're trying to understand UTK students? Why or why not? So if you know something about UT, you might be like, I don't know about that, Brian. What do you think? If we were to sample 10,000 UTK students, then I would say we don't pass it, because the 10% condition means we sample less than 10%. There's about 30,000 UTK students. Good answer, Roger V, right there. With 30,000 students, we couldn't sample 25. If there's 25,000, then we would sample at most that many right there. You can't sample more than 10%. Does that make sense? We can't sample more than 10% of the population. So our sample size could not exceed 2,500. I think Jessica given some good numbers right there. We don't want our sample size to be more than 10% of the population. That's the condition right there. Next one is based on the data we're doing. So what is the third condition here? This is where we put pause in the chat. So if you're with me in live classes, we always put some pause in the chat right there. And so we stop and we say we're doing categorical data. So we pause for a moment. This is categorical data. And if it's categorical data, the third condition is what? What is the third condition? What is the third condition? Think of SF. SF. Hopefully that jogs in your mind. You think SF. SF. So what's the third condition? SF. Success failure. Great job, Rod TV, right there. Success failure. So success failure says we need at least 10 successes, at least 10 failures. We have right here 15 successes, which is more than 10. So with 15 successes, there would be, and failure is not giving birth to twins apparently. There were that many failures. Good to see you, Christy. So we have 15 successes and 559 failures for the. Do we need a prototype on Friday? No prototype, because it's just a contest. Woo! Do we submit a video? No video. PowerPoint presentation. Peaks, good questions right there. No prototype, just a contest to see who gets the best predictions, and then a presentation to the company, the Galactic Empire. Oh my gosh, Star Wars. So state the null hypothesis. The null always has the what sign. This is a good hint for the test, but this doesn't help us. The null always has the what sign. The null always has the what sign, which it does here. The null always has the what sign. And we did some review of null alternative earlier, and Meath got it right there. The null has the equal sign, doesn't help. But they want to know, Is the rate of twin births the same among young mothers? So the null would be it is the same to what we see in the general population of 3.7%. But if we want to see if it's the same, the alternative would be which one of these, A, B, or C. So if the null is that it's the same, that it's equal to what we see in the general population, the alternative should be A, B, or C. So which one of these alternatives is right? We have to narrow this down by looking at the alternative. They're asking right here, their question is it the same? Jessica got it right there. Since we're asking, is it the same? The alternative would be, well, is it different? So the alternative is always the evidence-based claim, and you have to look to the question. Don't look to the data. Look to the question to say, well, they want to know if it's the same, so let's see if it's either the same or different. And that's how we test, write the alternative, by looking to what the question asks. Don't look at the data. Look at the question they're asking, and then we collect data. Now we're going to actually look at the data and see what comes out right here. Now, once again, I know people know this. A lot of these last few questions boil down to knowing the what. A lot of these last few questions boil down to knowing the what for these questions. A lot of these last few questions, last few chapters, really boil down to, oh, do we still have it?
I am Mubot.
Notation, brother.
It's still here. Notation, brother. Thank you right there. We got some notation, brother, in the chat. Okay, it still exists. And I lost my pen. There it is. Okay, so know that notation. 100 points right there, Michelle and Jessica. So the notation is as follows. Now, since we wrote null hypothesis P equals 0.037, that makes this value right here P naught. That is the hypothesized proportion. That is P naught. This value over here is N for sample size. That's X for amount of successes. And I think that's it. Now, if we have P naught, what else could we get if we know P naught? I know P naught is equal to... What could I get now? I'm going to solve it right here. Q naught, meet, excellent work, yes. So P naught and Q naught are complements. And we can get Q naught. So we have P naught and we have Q naught. They're complements, just like P hat, Q hat, or P and Q. Exactly 1 minus P naught. Great job, Jessica, put in the chat right there. So if you're wondering how I got that number right there, 0.963, these two numbers add up to 1. They are complements. Great job, Jessica, knowing how to solve for that. So now we're going to go ahead and solve the equation. I'm missing one thing. How can I get P hat? P hat stands for sample proportion. How can I get the sample proportion? X over N is sample proportion. And let's solve for it. Go. Great job, Jessica. Vanish. There we go. Let's get that Z-score. Is it possible to get a 12.4? It's possible. All RMSEs are possible. All RMSEs are possible. RMSE is just a typical miss the mean makes, or typical miss our model makes. Yep. Good questions right there. There we go. Square root. Almost forgot that. That's the standard deviation there on the bottom. Now we're going to take the difference up top. Something happened. I think I forgot a 0. Yeah, there we go. Negative 1.37. I was scared because we did 4.5 RMC and it came out too high. Well, it just depends on what you're analyzing. Negative 1.37. Or then 8 in my round. There we go. Negative 1.38. And so let's see. Z-score here. 2 decimals. And there we go. Now we need a p-value. Okay, where are we going to go for a p-value? Where are we going to go for a p-value? Anyone know, since we have a z-score, where do we need to go for the p-value? Where do we need to go for the p-value? The applet. Yep. We can kind of think about it a little bit here. It's going to be between... It's going to be about... It's very hard to get this one. It's a guess. That's a guess right there. Ooh, thank you, Meath, right there. Okay. I took a guess. And we have to put in the outside because it's a does not equals test. And so we go here and put the outside, and we get 16.8, 0.168. This is a very hard one to guess because it's between values I know, so it's hard to figure out exactly what it would be. Took a decent guess at it right here. It's actually 0.168, but that is a much harder one to guess than the ones we guessed earlier. You would need to use an applet to get a really good estimate of that. Now, if you look at this, we have a saying, when the p-value is low, blah, 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 blah. When the p-value is high, just let it fly. When the p-value is low, what do we say? Does anyone know my saying? When the p-value is low, the null must go. Yep, when the p-value is low, reject the null. When the p-value is high, just let it fly. So this p-value right here is higher than 0.05. So if the p-value is higher than 0.05, we just let it fly. Unless they specify a different alpha, which they didn't. The alpha is the bar by which you reject. So usually it's set to 0.05 and we are above it, we are higher. Our p-value right there that I'm on with the pointer is above 0.05. The p-value is high. You just let the null fly. So you would fail to reject the null. Woo! Getting scared on these. I think we got time for one more. I know there was a 474 question. We did some transformation last time. Student absent from school. Chapter 14. And we had people were wondering about transforming data. We did that during last office hours. We'll do another 201, then we'll try to do a little 474. Okay. I'm going to send a quick text right here real quick. Let's see. I'm going to head out today. Awesome. You're welcome, Rajvi. Good work there. Student absent from school. I remember this one. Student absent from school? Why? Why would a student be absent from school? Chapter 14. Absent from school? Medical researcher. Is it... Does anyone know where the student absent from school question is? Someone said student absent from school. Where is the student absent from school question? You asked about the student absent from school question. Let me know. Is it student attendance? There's one about student attendance. Okay, yeah. There's one about student attendance, and like they say it like dropped, but they would note any change in it. That is, they're looking at the percent of perfect attendance. So that's chapter 15, I think. And it's like, they look at percent of perfect attendance, and it's like it dropped in recent years from 31 to 30. The school would note any change in recent attendance. That one rings a bell. Like, is it chapter 16? So many. Let's see, one more song right here, and then. Sounds to me like chapter 16, hypothesis testing. This has got a lot of stuff. That's the one, yeah. Yeah. It's like they would note any change. I've done these questions a lot, if you can't tell. I'm like, okay, wait, what is that? What does this sound like to me? It's 15? Okay, it's 15? Let me go back to 15. I was in 16. Not like 15/16, is it? I thought it was in 15. Is it on the homework? Because maybe it should be on the quiz also. The quiz is supposed to have a thing of, oh my gosh, I think I was in the wrong thing. I don't like the way they've done this now. Here we go. Wait. Oh, this is the 1997 school attendance. This is the, okay, so yeah. School attendance. Chapter 16. Wait, the twin burst, was that chapter 16 also? I think. Okay. 108. Okay. Let's head over to it. It was 15. Thank you so much. It's going to help people in the future. And this is chapter 15 also. 100 points right there. Chapter 15 all day long. Let's go do it. Okay. Now, we've got some really great stuff here that we've been practicing today for doing the first parts of this. Anytime we write the null hypothesis, the null must have the what sign. Now, I'm not going to click on this yet. You should know when you write the null hypothesis, the null has the what sign. Anytime you write a null hypothesis, the null has the what sign. Anytime you write the null hypothesis, the null has the what sign. That's what we just practiced right there. Jessica knows right there. The null has the equals. Boom. Free points. Free points right there. Great job, Meets, right there also. Free points. So this is saying that the true proportion of perfect attendance, that students have perfect attendance, is 34%. Now, officials would be concerned if it declined. Do these figures indicate a change in student attendance? Do these indicate a change? So if we're asking, is it different, what should the alternative sign be? So the alternative is always determined by the question's wording. So if we're asking, is there a change? Now, don't look at the numbers to be like they declined. Look at the question. They're asking, is there a difference? The does not equals. Exactly. So the does not equals is the alternative because the question wording determines the alternative. Don't look at the data. Look at what they're asking, and then that determines the alternative. They break apart right here the random condition, or they call it independence. Sometimes they do that. If it's random, it is independent. Did they do this? Probably. Thank you, my Pearson. I'd prefer a yes or no. Is less than 10%? Well, this means they sampled less than 10% of all students. I'm guessing this is concerned to like all students across a larger population, so it seems as plausible. 10% is a weird one. Deals with finite populations. Success failure condition, because this is categorical. We usually like to say pause before getting to the third condition, because the third condition is based on the data you're working with. If you were working with quantitative data, the third condition would be nearly normal. If you're doing the chi-square test of independence, the third condition would be random 10%, count data, and cell count greater than 5. My brain had to slow down there. You see, my brain has to pause for a moment. We all pause, and we got to say, slow your brain down before you speak. That's what I have to do. So the third condition is data dependent. It's like, what kind of data are we working with? And then we can choose what the third condition is. So this is categorical data. Do students have perfect attendance or not? And then because of that, we're working with the success failure condition. Now this one we can actually check. We look at the data right here and we want to see how many successes there were in if the null was true, because we're going to use P naught. P naught is 0.34 because that's what we're hypothesizing it will be this year. It'll be the same as last year. So we take 34% of the sample size, 8736, and that's at least 10. Now, NQ naught would obviously be greater than 10 too. You can actually solve that pretty quickly by subtracting this from that right there, which is also just the same as doing Q naught times the sample size 2. So this was NP naught, which is sample size times hypothesized true proportion, and NQ naught, sample size times hypothesis complement of hypothesized true proportion. So make sure those are greater than or equal to 10, and success failure condition. If it's equal to 10, it's like, it's probably fine. Don't worry, we'll never put exactly 10 on the test. So this one is met. It's not a plausible. We can actually check that one mathematically. Perform the test right here, and you know what it comes down to.
Notation, brother.
It's all about that notation on the last question right here. All about that notation. We're going to grab this right here. Let's jump into it. Okay. So with this right here, let's take a look. We have right here this, and I think that's got it. In this type of question, how do you determine which one is P naught and which one is P hat? So P hat right here is what we observe in the current sample. So a randomly selected group of students. If this is the randomly selected students, oh, it does say random, so it is random. Would this be P hat or P naught? If those are the randomly selected students, would that be P hat or P naught? If those are the random sample we took. That's the randomly selected sample of students. So which one would that be? If that's the randomly selected sample of students, would that be P hat or P naught? What would that be? So that's the randomly selected sample. Good question, Meath, right there. That's our randomly selected sample. That would be, that's going to be P hat. Because this is what we're testing them against to see if this is true. So that's what we hypothesize is true. We're saying, is this sample different from what we've seen in the past? So the past is what we think we might see in the current present time. So the 1997 report, which is forever ago now, people probably born after that. I was in high school then. I'm old. It's funny. It's like, that's not old. And I'm like, I guess it is. And then this is the sample. And that's another good indication that anytime you have a sample, you should also have a what? Anytime you have a sample proportion, you should know it's what. If you have a sample proportion, you should also know it's what. If you have a sample proportion, you should also know your sample what. So a sample proportion would have a sample this. So if I had, well, it can have a complement. We can find Q hat, but the sample proportion will always have a sample size with it. Does that make sense? To say like we took 8,736 students. Well, that's our sample right there. And then we saw a sample proportion in it of this. So there was a sample size right here. And that's a sample proportion, which came from a sample size. Yeah, no worries. It's just practice right there. Jessica, excellent work. Good practice right there. We can find complements. And just going through and marking these and practicing the notation, understanding what P naught and Q naught mean. There's a lot like P hat, P naught, Q hat, Q naught. There's a lot to remember right there, like when it comes to like which one's which. So I understand how they're different, and it really comes down to practicing what the notation means. So now we just solve the problem. And that's the z-score. Let's check it out. Oh. Well, I basically know it now. 1.97 negative. So this is rather interesting. Meath, we're going to be able to figure out the p-value here. Negative 1.97. Meath, do you have any idea what the p-values are going to be a coup for the... Yes, of course. Yeah, no, good question right there, Jessica. Thank you. Yep, we'll have a coup for the final. Thank you so much. We're definitely doing that. Probably maybe this weekend, maybe. Might be a good time. Be coming up right here. Maybe on Sunday. Might be good. So, Meath, do you have any idea what the p-value will be? And I want you to see what this looks like. I want you to see what this is going to look like right here. Well, this time, now we're using a z-score, so we can actually use z-scores. So we landed at negative 1.97. And we need to shade the area here. And then we need to shade the area. It's supposed to look symmetric, but I can't draw today. Over here. Let me redraw that. It's the worst normal curve ever. Oh my god. It's not getting better. Sure. Normal curve looks skewed. I just need to redraw it from scratch right here and do my normal curve like that. And now go over here and do this and this. And it should be symmetric around it. So, Meet, does this help give you an idea? Because we're almost at -2 and 2. We're almost at -2 and 2. The answer is going to be very close to what percent? Because we're almost at -2 and 2. It's very close to that. So if we're almost at -2 and 2, it's going to be about this. We could probably guess that and get it right. 5%. Yep. 5%, because inside of -2 and 2 is 95%. Or more exactly, 1.96. So 5% would be outside. So that's how we can use our knowledge right here to say it's going to be about 5%. We might get it right. We'll find out here in a moment. I always like to take a guess at it and use my knowledge. Why not? Since we're on this and we're running very short on time, we're going to go look at the David M. Lane. So what you want to do with your z-score right here is you want to take the z-score, go to the David M. Lane, plug in the number, and remember what way you're doing the test. We are doing a does not equals test, so we need to shade the outside. It's 0.0488 or 0.048, so or 0.049. So I think we probably would have got it correct. It's 0.049. I think that in the margin of error we would have gotten that right. So probably would have gotten it right. So now we use an alpha of 0.1, which is a little different. Is our p-value above or below 0.1? Is our p-value above or below 0.1? So p-value right there, above or below 0.1. Here's our p-value. P-value's here. Alpha's up here. The p-value is lower than 0.1. So we reject the null. There is evidence to the alternative. So this is the way the phrase has to go. Reject is evidence. Do not reject is not evidence. If you have not rejecting, there is not evidence. This means fail to reject right here. So I do not reject. I do not have evidence. I do reject. There is evidence. And you reject when the p-value is lower than alpha. You do not reject when the p-value is higher than alpha. If it's right at it, we've got advanced ways to deal with that, and we won't do that to you on the test. In technical sense, I should say this. You reject when the p-value is lower than alpha. You fail to reject when the p-value is at or above alpha. So if you hit alpha right on alpha, you don't reject in the classical sense. We do have advanced ways of dealing with that, though, which we don't do in 201. Sufficient evidence to conclude has changed. This is evidence to the alternative that it has changed. And do you think the difference is meaningful? It's only 1%. I hate this last question, but they're just asking, is this a practically significant difference? The difference is probably not meaningful. We saw a very small change. And so let's check our answers, 100%. And if we had guessed 5%, we would have gotten it right. And that's what I like right there. Meath, great job. Meath, 500 points for practicing knowing the empirical rule. That's why I carry the empirical rule around in my head. So that way I can always like take a guess at what the p-value will be. And I can always do these quick little sketches and be like, okay, so it's going to be close to 5%. And if you have this understanding, a lot of times you don't need to use the applet, because if I were to tell you I ran a statistical test and I got a z-score equal to 5, what would you tell me about the p-value instantaneously? Like, if you know I ran a statistical test and I got a z-score of 5, you could probably guess the p-value like that. Like, boom, Meath, you just did it. Yep. As long as we're doing either a greater than or does not equals test, you're way off the curve. You would be all the way over, 1, 2, 3 right there, 4, 5. If we actually put this on the right scale, but you'd be so far off the curve that there'd be no area beyond this. That's a horrible drawing, but That's the kind of, yeah, we're way above. It's extremely far away. So we'd be so far away. I'm not drawing my curves right. It'd be so off the curve that it just can't happen. So that's the kind of understanding you want. If someone says we have a z-score of 5, you're like, wow, that's a crazy result. Because the test will give you the result. If you know how to read output, you can just go right here and run a t-test. So if we go t-test, and we do the iris data set, and we get a t-score of 86, I'll tell you what the p-value is. It's 0. That right there stands for 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1. This is the p-value. Oops, I did one too many. That's the p-value right there, which is the smallest p-value estimates. You're welcome, Jessica. So since I saw this t-statistic of 86, it's just telling me the p-value is basically 0. I wish it just said 0 in that output. Really good practice here, everybody. Great job today. We'll be back tomorrow. Keep up the great work. Keep asking questions. The last bit of material in the class is some of the toughest stuff. That's why you just want to keep doing the homework, keep doing the assignments, turn in the project. Test is challenging, but remember, all the work you do beforehand is going to buffer you for that test. You got this. You guys, everyone. Bye.